Hi everyone! In this video, we will be sharing our work, Linear Mechanisms for Spatial-Temporal Reasoning in Vision Language Models, to be presented at ICLR 2026. This work was performed at Caltech by Rafi Kang, Hongjia Chen, Georgia Joksori, and Pietro Perona. This paper was motivated by an observation many of you have probably already made. Increasingly, autoregressive VLMs exhibit compositional reasoning capacities. What do I mean by that? More specifically, image VLMs can perform simple spatial reasoning. So given a prompt like this, latest closed and open source VLMs all correctly answer the question. Similarly, video models exhibit ability to do simple temporal reasoning. So given a video and a query like this, all video VLMs tested can answer correctly. So how do they do it? One could ask the question at a data level or architectural level, but we are specifically interested in the representation space. How do we go from raw pixels and tokens to some intermediate representations, which then yielded the correct token answer? We start with a hypothesis that there must be some linear mechanism that transfers spatial localization information from the image patches to the text tokens, and finally to the linear readout layer. This is empowered by the linear representation hypothesis in LLMs, which suggests that high-level semantic concepts are encoded as linear directions or subspaces in neural network representations. Let's first focus on spatial reasoning in 2D VLMs, and we can come back to temporal reasoning later. To characterize a linear mechanism for spatial reasoning, we first step through what happens during a VLM forward pass. Given a query in an image, the model patchifies the image and tokenizes the text. The text tokens and image patches become embeddings with the same embedding dimension and are concatenated along the sequence dimension. This concatenated image and text sequence goes through L attention blocks in the VLM, yielding a matrix of logit likelihoods for all tokens in the vocabulary. To characterize what happens in the latent space to enable this reasoning, we first look at how information flows across modalities. To do that, we set up the mirror swapping experiment. In this experiment, for each image and spatial query, we have a mirrored counterpart. The mirrored counterpart is exactly the same prompt, except the image is mirrored horizontally. Since the image was mirrored, the model's output logics should also be opposed. Zooming in on the activations from some random layer should enable a view of these patch and token level latent vectors, and you can see that the token activations are all the same, whereas the image patches will be reversed. Now we introduce 3 swapping interventions. At some intervention layer, we can create these swapped activations, one where we swap out all text tokens from the original case with those from the mirrored case, another where we swap out all image tokens with the mirrored case, and a third swap where we swap out just the object word tokens with those from the mirrored case. After performing these swap interventions, we let the swapped Franken activations go through the rest of the VLM unperturbed and monitor the output likelihoods for the left and right logics. Here we share the results from the experiment. A value of 1 on the y-axis indicates that the model belief is exactly the same as the mirrored case, and a value of 0 means that it was unchanged from the beliefs in the unmirrored original case. We see that swapping out the text tokens at any layer before 10 does not impact model belief, while after layer 15, model belief is entirely swapped to match the mirrored case. In contrast, model belief is only swapped if the mirror swap happens before layer 10 on image patches and has no effect after layer 15. And if we swap object words, we see that only between layers 10 and 15 the model's beliefs are acutely changed, but afterward there is little effect. So we observe that instead of a smooth, continuous flow of information from image patches to text tokens, there is an abrupt transitionary period where the modalities merge. And spatial information seems concentrated in object words only in this region. We also share some controls for the experiment. First, we want to check if the effect is really a result of spatial mirroring. So we conduct the same swapping intervention, but instead of mirroring the image, change the colors in them. We see that this type of intervention yields mostly noise, and not the clean binary belief swapping behavior observed from mirror swapping. We also want to check if object word tokens are actually special. Here we see that the result of mirror swapping on object word tokens compared against random tokens are clearly more consequential. So now we know that in VLMs, spatial information flows from image patches to text tokens in modality merging layers, specifically onto object word tokens. The new question: how exactly is this spatial information represented? We start off with the assumption that spatial localization information is saved linearly on object word tokens and perform extraction and steering experiments to characterize that model. To begin, we can derive spatial IDs from synthetic data. We take renders of random 3D object assets and place them on a 4x4 grid. We used 90 object pairs, which resulted in a total of 86,400 images. With these synthetic images, we can derive spatial IDs by querying the VLM with an image where the object is in some specific coordinate, 0, 0 in this case, and extract the word activation for that object at the intermediate layer. To get the spatial specific component, we first compute the semantic component by taking the average of the object activation across many different object locations. If we take a single instance of the object word activation and subtract the average, we can isolate the spatial component. We average these across a bunch of the different objects that were the 3D renders shown in the previous slide. Now these extracted IDs can be projected onto a shared spatial coordinate axis. We see spatial IDs for lava and llama here, for example, and they exhibit a clear organization by spatial coordinates. Now that we have extracted these spatial IDs with synthetic images, steering on real images is pretty easy to do. In this specific example, we have this image of the potted plant and a bottle. The dotted blue line shows the model's original likelihood of saying left, and the solid blue line shows its likelihood of saying right. If we add a rightward spatial ID on the plant word token, and a leftward spatial ID on the bottle token, somewhere between layers 10 and 15, we can see that the likelihood of the model predicting left goes drastically down. We can observe this effect at scale by taking 100 samples from cocoa. Given a query like, is the subject to the left or right of the object, adding spatial IDs towards the right makes the model increase the probability of responding right, and vice versa for left. Whether the original image depicted the subject being to the left or right does not matter. We can perform this steering for different query types such as near or far or in between, etc. We performed spatial ID extraction and model steering across 11 open source VLMs. For all of them, we find that spatial IDs can acutely alter model beliefs much above chance. Median binary belief swap due to spatial ID steering is 64.4% and 29.5% for noise. Spatial IDs have a 43.6% above chance influence on average. So now we see that in VLMs, spatial IDs bind to object word tokens and causally mediate model beliefs. This way, the model is able to perform linguistic reasoning among text tokens only in later layers without using image patches. So, how does knowing about spatial IDs help VLMs? In other words, what are the applications? First, spatial IDs help us diagnose depth representation limitations in VLMs. In lava, the spatial IDs that drive differentiation between above and below are strongly correlated to behind and front. When projected onto the principal components of spatial IDs, they almost entirely overlap. This gives us a hint about why depth-related reasoning might not work well in 2D VLMs right now. Second, spatial IDs help us diagnose model bottlenecks. When a model fails, why does it fail? It could be a bad vision encoder, bad cross-modal spatial information transfer, or wrong spatial ID inference. Doop, doop, doop. We can perform this diagnosis on llama and lava models as a test case. So working backwards, if the model didn't know how to use spatial IDs correctly, whether it found the correct spatial ID of an object or not wouldn't impact whether it gets a sample correct or not. In llama and lava, we actually find that samples that the model got wrong were also samples that the model had bad spatial IDs on. So it was not the case that the models didn't know how to use spatial IDs. But where did these wrong spatial IDs come from? A bad vision encoder or bad spatial ID integration? To identify if the vision encoder is a problem, we can perform a bounding box blurring test. If the vision encoder was good, it would be more sensitive to blurring the object than some random area. Results from the blurring experiment show that the samples lava got wrong were wrongly detected by the vision encoder, while llama's vision encoder did not behave differently on the samples that the model failed on. So in this particular case study, we can conclude that for lava, the vision encoder is likely to have failed at object detection in the cases where the models failed. But for llama, the vision encoder didn't fail in the wrong cases, so the issue must lie in the cross-modal integration of IDs, since the model does know how to use IDs correctly at inference. The third application of spatial IDs is improving model spatial reasoning performances. So if you recall from a previous figure, some models were more readily steered with spatial IDs than others. We find that model accuracy in COCO spatial scales with how well that model is steered by spatial IDs. So if you want models to be better at spatial queries, we should promote spatial ID learning during training. Fine-tuning Quen 2B checkpoint on synthetic data to promote better spatial ID organization results in faster convergence and higher validation accuracy on COCO. Here, the spatial ID loss computes the cosine similarity between the predicted and ground truth spatial ID in an intermediate layer. As a finishing touch, while our work didn't focus on video models, we did find that these experiments can be repeated on video models. With synthetic videos and real scenes from movies, we can perform temporal mirror swapping, ID extraction, and steering, and find that similar to spatial IDs, temporal IDs mediate model beliefs about the ordering of events through time. So in conclusion, autoregressive VLMs exhibit compositional reasoning capacities by linearly encoding spatial or temporal IDs into word activations in modality merging layers for efficient readout. You can find the archive link to our paper here and our GitHub repo. Please feel free to contact us with any questions, suggestions, or ideas. Thank you for watching the video and taking interest in our work. Bye-bye.